Okay, let's talk about absolute extrema. Not one of my favorite topics, but we need to talk about it. Let f be defined on an interval I containing c. F of c is an absolute minimum, or amin for short, of f on I if f of c is less than or equal to f of x for all x in the interval. Now, f of c is an absolute maximum, or a max, of the function on I if f of c is greater than or equal to all functional values, or all f of x in the interval. Now, some functions don't have absolute extrema. Okay? These functions here, this function continues to increase without bound, or decrease without bound, and so does this one. So both of these functions increase and decrease without bound. So they actually wouldn't have any absolute extrema. Let's read this little discussion here. Relative extrema are actually the largest or smallest values in a local area or neighborhood, where absolute extrema are the largest or smallest values over the entire graph, if they exist. And as I said, many graphs have no absolute extrema. But if you look at a graph on a closed interval, they must have absolute extrema. Actually, they must have an absolute maximum and an absolute minimum over a closed interval, and this is stated later. So if we just say minimum or maximum, we're actually referring to the absolute extremas, absolute min, absolute max. So to refer to relative extrema, we need to state the word relative in front of them. Now, some other texts might use global instead of absolute and local instead of relative. Okay, here's the extreme value theorem. The extreme value theorem says if f is continuous on, and this is a closed interval from a to b, then f has both an absolute minimum value and an absolute maximum value. So for instance, let's say that we went from here to here. Let's say I wanted to draw a graph that was continuous between these 2 points. So let's say I want to draw any graph I want to. I can go up and down, or I could go straight across, or but I just want to draw a graph that connects these 2 dots. Well, the extreme value theorem says that over this closed interval from a to b, you've got to have both an absolute maximum and an absolute minimum. Now here, the absolute maximum occurs at this peak, and the absolute minimum occurs at this valley, because this is the highest point on the graph over the interval, and this is the lowest point over the graph. Now there's some other points that are relative extrema, but basically we're talking about absolute extrema, absolute maximum and absolute minimum. So the guidelines for finding extrema on a closed interval. Now when I talk about extrema, I'm talking about the absolute extrema here. So I probably should have wrote in there absolute extrema. So to find the absolute extrema of a continuous function on closed intervals, follow these steps. Okay? So, and let me explain to you why we follow these steps. Obviously, you need the critical numbers. And make sure you stay within the domain of the interval. And then you evaluate the function at each critical number. But you also must evaluate at the endpoints. So let me show you why. Like if we got the critical numbers for this function here, well, we would get we'd get a critical number here at that valley. We'd get one at that peak. We'd get one here at this valley, one at this peak, one at this valley, and one at this peak. But the endpoint might also be the extrema, because what if the graph ended, say, down here? What if the endpoint was down here? Well, then this endpoint would be the lowest value. Or what if one of the endpoints ended way up here somewhere? Well, then that would be the highest value. So not only do you have to check the critical numbers over the closed interval, you also have to check the endpoints of the closed interval. And then whichever values give you the largest number, that largest number is the absolute maximum, and the smallest of those is the absolute minimum. So let's take a look at how we can solve some examples there. Okay, so 5 minus 2x squared, but I'm only going to look at it over the interval -2 to 3. So first thing I do is I get my critical numbers. The derivative is -4x, so 0 is a critical number. Okay, now let's make sure, does 0 lie within this interval? Yes, it does. So yeah, we're safe. All right, so evaluate the function at the critical number x equals 0. So now I'm just going to plug 0 into the function. So plug 0 into this function and I get 5. Okay, that's the only critical number. Now I have to check the function at each endpoint. So let's check the endpoints. At -2, let's plug -2 in. 5 minus -2 times -2 squared. That would be 5 minus 2 times 4. So that's 5 minus 8, which is -3. So I get -3. The other endpoint, plug 3 in. 5 minus 2 times 3 squared. So that would be 5 minus 18, which is -13. So f of 3 is -13. Now, look at these three numbers, 5, -3, and 13. The biggest of these three numbers is your absolute max, which is 5. The smallest of these three numbers is your absolute minimum, -13. Now, if you look at this graph, to verify this, make sure you only look at it, only look at the portion where x goes from -2 to +3, because the portion outside of that range is irrelevant. Okay, here's another graph, and then the interval we want to consider, or the interval we're looking at, is from 0 to 4. So first find the critical numbers, take the derivative, and then set the derivative equal to 0. You should get plus or minus 2 for critical numbers. Okay, but only one of those falls in this interval that we're given. So -2 I don't need to check. So I only check +2 because -2 is not in that interval. So let's check +2. Well, f of 2 would be, let's see, I would get 8 minus 24, that's -16. And then the endpoints, what's f of 0? F of 0 would give me 0, and then f of 4 would give me 4 cubed is 64, 12 times 4, 48, 64 minus 48, 16. So, here are the three numbers, -16, 0, or 16. All right, which one's the largest? 16. So the absolute max is 16. Which is the smallest? -16. So the absolute minimum is -16. Okay? All right, here's one more. This one says over this interval. Now I did this on purpose because I knew we had a critical number of -2/3 between 1 and -3/4. So I wanted to make sure I did that. So anyway, we did this a couple times earlier. We know if you go back and look at the previous notes, you'll see that these are the critical numbers for this. Okay, -1 is not in the -1 is not in this interval. So just don't even worry about -1. Okay, so now evaluate this function at -2/3. Well, if I plug -2/3 in here, and I grabbed a calculator to figure it out, I got like -0.385. Okay, then I'm going to check the endpoints. If I evaluate this function at -3/4, I got -3/8 or -0.375. And then if I evaluate it at the other endpoint, 1, I actually got square root of 2, which is about 1.414. So actually, the smallest of these three values is -0.385. So this would be the absolute minimum. And then the absolute maximum would be the largest of these three values, which would be, and these are just approximations here, 1.414. Now, I'm going to end this section with just a little application here. I've always thought this was an interesting application. It says coughing forces the trachea to contract, which in turn affects the velocity of the air through the trachea. The velocity of the air during coughing can be modeled by this formula. Velocity equals K, which is a constant, times the quantity capital R minus small r times r squared. And it tells that little r has to be between 0 and capital R. So now I told you K was a constant. Now R is the normal radius of the trachea. So if this was you we were talking about, whatever your normal trachea radius would be, that's what R would be. So R is also a constant. It just depends on who we're dealing with, on what the number is. Okay, so, and little r is the radius of the trachea during coughing. So basically what we have here is a relationship between the velocity and the size of one's radius, or the radius of one's trachea during coughing. Okay, so I want to find what radius will give me maximum air velocity. So I want to maximize velocity. Okay, well, first of all, I know that the derivative, if I take the derivative of velocity with respect to little r is the variable. So if I take the derivative of this inside here, okay, the derivative of this inside here, what's the derivative of little r squared with respect to little r? Wouldn't it just be 2 little r, 2r? And then we have this other constant, big R. So we have 2r, 2 big R, little r. And then minus r cubed. So what's the derivative of r cubed? Now remember, r is our variable, so we're differentiating with respect to that variable. So that would be 3r squared. And then I just bring the constant down. So now that's my derivative. So now let's set the derivative equal to 0. Okay, so I'm going to set the derivative equal to 0. Now you might notice I factored a little r out of this when I did that. So I did two things at once here. So I factored the small r out of here. And then what I'm left with is 2 times capital R minus 3 times little r. And so I basically get constant times r has to be 0, or 2r minus 3 little r has to equal 0. Well, the constant I'm going to assume is not 0, so for the constant times r to be 0, then little r would have to be 0. Okay, but I don't think that would make sense, because if little r was 0, that would mean that your trachea has no radius. So I don't think you could get any airflow there. So that's probably where you minimize airflow. All right, so let's try the other one. 2r minus 3r. If I solve this, in other words, if I solve this algebraically for little r, and you can do this on scratch paper, but if you solve it for little r, you're going to get little r is 2/3 of capital R. Now, this is the actual one that maximizes airflow or maximizes velocity. So if you want to know what radius the trachea needs to be, it looks like it needs to be 2/3 of its normal size to maximize air velocity. So the radius must be 2/3 of its normal size, and that maximizes air velocity. And we'll see more of these in the optimization section. Okay, so that pretty much covers Extrema. The next section we're going to get into another topic that's called concavity and points of inflection.